Hello students. So in today's class we are going to start studying about the combination of resistors. Resistors, as we have seen, provide resistance. Resistance to the flow of current. So these resistors are the electronic equipment providing resistance to flow of current, and when they are combined in different ways, their power to resist fluctuates. What all are the combinations in the resistors we need to understand. First combination is series combination, and the another combination is parallel combination. A series combination of resistors, or as we are going to study in the next class about the cells, states that these are connected serially in a single line, like you stand in a prayer line, 1, 2, 3, very systematic. Whereas parallel combination says that they are parallelly aligned. Parallel lines are the lines which have the same direction but are away from each other, and they do not meet at any point. So when we say our resistors are combined parallelly, we aim that resistors are combined up and down and are connected through the junctions. See, over here is the junction and are connected through the junctions. It is not always that a parallel connection will look like this. No, a parallel connection may look like this. So in this connection also, these two are parallel, and whatever combination we are getting out of these two will be in series with the third resistor. So in our class we will read the various combinations and how we are getting the effective resistance. And later on, while solving the problem, we will solve the various combinations to understand and improve our quality in understanding these combinations. So we'll get start with our first concept, that is resistors in series. Now our resistors are serially arranged. You can see the figure number 1, which is showing series connection of now. Maybe the first question arising in our mind is, why do we need combination? Why do we need combination? So just think for a situation that in our electronics shop or lab, electronics shop or lab, wherever we are working, we only have 1 kilo ohm resistor or 10 kilo ohm resistor. We are assuming, but now we want 9 kilo ohm, or we want 12 kilo ohm, or we want 2 kilo ohm. We want these resistance. How can we attain these values? For attaining these values, we need to combine these resistors. In case we are having smaller value resistor. Smaller value resistor, but combination of greater value is needed. Combination needed for big value. What we gonna do is we will serially arrange our resistors. But see the upper side. In case we have bigger value resistor and we need to get a smaller value combination, what we gonna do is we will add these resistors parallelly to each other. Parallel combination will be made. Now we have understood this question. Now let's start and understand how series connection is giving us a big combination and how parallel combination is giving us a smaller resistance. So see the diagram. First of all, here we are having a resistor R1 and the another resistor R2. Throughout this, current flowing is I. Diagram is extremely important. Kindly pay a greater attention in this case because this diagram will be helping you. Okay, so here we'll see that from A to C and C to B, current flowing is same. Current flowing is I, but the voltage, applied voltage from A to C is V1, whereas C to B is V2. There is change in voltage V1 and V2. Consider two resistances R1 and R2 connected in series and potential difference V is applied across them. Charge which leaves R1 must enter R2. What is current? Current is charge per unit time. So the charge which is leaving the resistance 1 will enter the resistance 2. Hence current is same. This line supports that current is same. Since current measures the rate of flow of charges, current I through both the resistances are equal. Now potential difference across R1 is V1, that is potential at A minus potential at C. That's how change in potential is given. Potential at initial end minus potential at final end. That is equals to current into the resistance of 1. From where is this formula coming? This is being derived from Ohm's law. This is being derived from Ohm's law. What is the Ohm's law? Ohm's law states that V is proportional to current, and to remove the proportionality we have V equals to Ri, where R is the proportionality constant. Moving next, potential difference across the R2 resistance number 2. We have V2 equals to Vc minus Vb, that is equals to IR2, current flowing through resistance 2 into the resistance 2. Now potential difference V across the combination, across the whole combination A, C and B, this is B. So across the whole combination will be V equals to VA minus VB. This is our initial state, this is our final state. So initial minus final. And we know that this VA can be given by this VA minus VC plus VB can be given as VC minus VB. See, I'll explain it. We got this. Now I will open this bracket. Okay. When I'm opening the bracket, I will get VA minus VC plus VC minus VB. This and this will get cancelled. What are we going to get? VA minus VB. That's how we are substituting these values. Okay. VC will get cancelled. So we know why we are substituting this value, bracket value, because we know the magnitude of this bracketed value, which is IR1. So I will put here as V equals to IR1 plus IR2, and here current in the both cases is common. So I will take I out of the bracket, and inside the bracket we will have the two resistance, that is R1 and R2. See over here, that is what we are getting. So this is what we will get as the potential across the combination. Now equivalent resistance of the combination Rs equals to equivalent potential divided by equivalent current. I'll erase this so that I can explain. See, we are having resistance in series equals to potential of the combination divided by the current of combination. Current of combination equals to I, whereas potential of combination equals to VA minus VB, which is equals to IR1 minus IR2. And as we are adding it up, okay, as we are adding it up, this will be plus. So we will get I into R1 plus R2. So this is V equivalent. Now we will substitute this V equivalent and this I equivalent in the equation, this one. So Rs equals to I into R1 plus R2 divided by I. Hence I and I will cancel, giving us a value Rs equals to R1 plus R2, which is the equivalent resistance or resistance for combination. Resistance for combination. Okay, hope you understood how we have derived it. Now see, here we have mentioned only resistance 1 and resistance 2. In case we are getting n number of resistance, then what will happen? If n number of resistance are connected in series, then the combination will be given by this formula. Rs equals to R1 plus R2 plus R3 plus dash 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 up to Rn. nth number of resistance. Now we'll move next further, that is resistors in parallel combination. In parallel combination. So in parallel combination, as you can see the figure number 2, this shows the parallel combination of resistor R1 and R2. So what is happening over here is, this is A point, this is A point having a potential VA, this is B point having a potential VB. From here, from this point, current is flowing. The current which is coming up to this junction is I. Here there is a split of the junction. In this case, the current number of charges per unit time will be different. Some will go up, some will go down. So the current in both the arms will be different. Over here we will get current I1, that is current one type current I1. Here we will get the another amount of current, that is current I2. Why so? Because here it is not ideally possible in a junction that the number of charges flowing per unit time to be equal. It can fluctuate, it can be same or anything, but we will always consider an ideal situation where this is the I1 current and this one is the I2 current, because there is a junction. Division over the junction is happening. Now this current is flowing through R1. From R1 it is I1 and from R2 it is I2. Current is flowing. Here again at this junction, current I1 and current I2 meets up to give the current I. So we can write a statement. See the statement over here, I equals to I1 plus I2 after they segregate at junction. After separating at junction. But in this case, the voltage among these points is same, because this diagram can be reconstructed as, see, diagram reconstruction. This diagram can be reconstructed as resistance 1 and resistance 2 having a potential VB over here and VA over here. So what it is saying, that the potential difference across both the resistors in the parallel combination is same. I'll write over here V across R1 and R2 is same. I have reconstructed the diagram for your better understanding. If you see diagram like this, you will see that whatever potential is going in this direction, same potential is going in the another arm R2. So there is no potential, there is no different potential at R1 and at R2. Both are having same potential. Now we will start up with the notes. We have understood the diagram. Now it's time for us to derive a combination formula where our resistors are connected parallelly. Now consider the two resistances R1 and R2 as we did in the previous case, connected in parallel across terminal A and B. The charge flowing in A from the left flows out partly through R1 and partly through R2. We do not know what amount of I1 is flowing and what amount of I2 is flowing. I1 can be greater than I2, I1 can be smaller than I2, and I1 can equal to I2. We are dividing the current as per to the law which we will be studying in the upcoming sections. It's generalized that we need to divide. But we are not assigning what amount of current is going in the upper arm and what amount of current is flowing through the lower arm, because that depends upon many factors: amount of voltage applied, magnitude of resistor, and how many connections are present inside the given circuit. So because of all these factors, the magnitude of I1 and I2 will change. Coming up to the third point, current I flowing in at A flows out as I1 and I2 through R1 and R2 respectively. Hence, it is right to say that I equals to I1 plus I2, or we can say that I1 and I2 are partial component of the overall current flowing through the circuit, that is I. Potential difference between A and B by applying Ohm's law is given by V equals to I1 R1 across the resistor R1, because here V is same but current is fluctuating. Potential is same but I is different. Now similarly, potential difference between A and B by applying Ohm's law to R2, we will get V equals to I2 R2. I2 R2. And see over here our first equation. From here we know that I equals to I1 I2. From here we have to substitute the value of I1 and I2. From where are we going to get the value for I1 I2? That is from here. This will give us I1 equals to V upon R1. We will substitute over here, and from here we will get that I2 equals to V upon R2. Substituting these values, V upon R1 plus V upon R2. We will take the common out. Over here common is V. V is a common component. Common. We have taken it out. What we are left with is 1 upon R1 plus 1 upon R2. So what is it equals to? It is equals to total current I. This is total current. Now, what is total current equal to? See, if the combination is replaced by equivalent resistance Rp, then by Ohm's law, total current equals to total voltage applied divided by the total resistance in the circuit, or the equivalent resistance Rp. See, total current equals to total potential divided by the total resistance. Over here, resistance is our equivalent resistance. What is equivalent resistance? It is the combination of both R1 and R2. So see the formula over here. I equals to V upon Rp. Now from here we have got I. We will substitute this in place of I. We will substitute this equation in place of I. Now let's see the results. We will get 1 upon Rp equals to 1 upon R1 plus 1 upon R2. See, I equals to V upon Rp, and the previous equation was I equals to V into 1 upon R1 plus 1 upon R2. Equating these two equations, we will get V upon Rp equals to V into 1 upon R1 plus 1 upon R2. This V and this V will cancel out, giving us this formula. This formula is for parallel combination. Parallel combination of resistors. Now this can be reciprocated. Here we have done reciprocal and it gives Rp equals to 1 upon R1 plus 1 upon R2 to the power minus 1. If n number of resistances are combined parallelly with each other, then the equivalent resistance can be given as Rp equals to 1 upon R1 plus 1 upon R2 plus dash 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 1 upon Rn to the power minus 1, or this can be written as 1 upon Rp equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus dash 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 up to the nth number of resistor. When resistance are connected in parallel, their equivalent resistance is smaller than the smallest resistor among them. It is smallest among the smaller comparing to the smallest also. If in parallel combination, we are having resistance R1, R2, R3, R4. Okay. So in R1 we are having 6 ohms, 5 ohms, 7 ohms, 8 ohms. What will be the Rp over here? It will be smaller than 5 ohm. Smaller than or equal to 5 ohm. But it will not be greater than that. But if the case is of series connection, if resistors are connected in series and we are having same R1, R2, R3 and R4 resistors having a value of 6, 5, 7 and 8. So in this case the combination will have resistance, like combination of these resistors will have resistance greater than or equal to 8 ohms, bigger than the biggest one, bigger than the biggest one. So this is how the combination of the resistors helps us in case we are not having that particular resistor. Now one thing I wish to show is the combination of parallel. N combination in the parallel will be connected like this. And then the last one, if I'll show over here, here many will be there. Okay. So this is the combination of N resistors in parallel. So that's all in the today's class of the combination. Now we will just go for a quick recap what we have studied in today's class and we'll end it up. So we have studied the combination of resistors, combination of resistors. In this we are having two combination. One is series combination and other one is the parallel combination. The circuital diagram for the series combination looks like this, and for the parallel combination it looks like this. If we say that this is resistance R1, R2, and over here also if we name it as R1 and R2, we will have three potential differences over here. Here it is VA, VC and VB. Over here we will have only two potential, VA and VB. Here across the whole circuit we will have the same flow of current, that is I. But here in this starting for the combination we will have I. Once there is the split of the arms we will have the current I1 and I2. Same goes over here, I1 and I2, and it comes out as I. From the Ohm's law, that is the basic law, we know that V equals to Ri. From here we will derive all these combination resistance and parallel resistance. So the potential difference across the whole system is given as V, which is equals to VA minus VB, which we can attain as in the fraction potential across A and C minus potential across C and B. So potential across A and C is VA minus VC, and the potential across C and B will be giving us VC minus VB, and it will give us VA minus VC plus VC minus VB, where VC and VC will cancel out, giving us AB minus VA minus VB. So we have derived how we are getting this, but the important formula for us is this. Important formula for us is this. From here we have VA minus VC equals to, here under consideration is R1 into the current I. Similarly, VC minus VB equals to R2 into the current I. This is for VC combination. This is for AC combination. We will substitute these values in the respective brackets. We will get from this equation, we will get V equals to R1 plus I, R1 into I plus R2 into I. This will give us V equals to I into R1 plus R2. And from Ohm's law we know it is Ri, which is equals to Ri. I and I being the common cancels out, giving us that resistance which are in series combination equals to the numerical addition of all the resistance, that is Rs equals to R1 plus R2. Now here the combination Rs will be always greater than or equal to R1, R2 or any number of resistors present. Okay, I'll just rewrite it. Rs is greater or equals to R1, R2, any number of resistance present. And for the resistance for N, we have R1 plus R2 plus R3 up to, we will add up to the nth number of resistor under consideration. Now we will go to the parallel combination. Here we can see that VA minus VV equals to the potential difference. Only one potential difference across both R1 and R2. Now across R1, current flowing is equals to I1, and across R2 current flowing is I2. Now we know that this potential can be written as V equals to we are having the same potential across this and across this. So the common formula is V equals to Ri. Over here we know that I equals to I1 plus I2, because here see this same I is dividing into I1 and I2. So from this formula we have V equals to R1 I1. Similarly V equals to R2 I2. From here we have I1 equals to V upon R1 and I2 equals to V upon R2. Substituting this value over here, we will get I equals to V upon R1 plus V upon R2. This I equals to VRP. So V upon RP. V being the common in all the three will cancel out, and we will get 1 upon Rp equals to 1 upon R1 plus 1 upon R2. That is the resistance in parallel combination. And another thing which we have seen is Rp is smaller or equal to the smallest resistor present in combination. Hope you have enjoyed the today's class. It is very basic for us to understand what is resistor and how their combination can be useful to us. So this class is all about the usefulness of these resistors and their combinations, and this part will help us further in solving many applications such as Kirchhoff's law, Wheatstone bridge combinations, and many more, where we will be applying these formulas very gladly. So I'll wrap up today's class. Hope you enjoyed it and learned something new today. Have a good day. Bye bye.